Well, two topics today, Mr. Sams.
Graham crackers.
Oh, the big Billy Graham.
Yeah,
Graham crackers and Dalton's Laws.
Yeah.
Actually, it's not Billy Graham, though.
No.
It's some other guy named Graham.
Yeah.
I forget his first name. What
I
is
don't
it?
know.
Yeah, so
No
Grahams?
idea. And Dalton.
Dalton. John Dalton. I do
That's
know that.
the Dalton of the atomic theory.
Yeah,
is it
same
not?
dude.
Yeah.
So we're going to talk about those things today. And so I think we'll start with a quick video clip about Graham's Law.
Okay.
All right.
Do you smell that?
Ooh, yes.
Gosh,
What?
it's like diffusing out of the biology room.
Dead things.
There's probably dead things.
We should figure out what's in there.
Let's go see what it is. Oh, gosh. Miss Papadakis, do you have dead things?
Yes, dead cats.
Dead cats.
Dead cats.
Are you dissecting them for anatomy?
Yes.
That's disgusting. Well, you can smell the dead stuff. What do they preserve them in these days? Is it still formaldehyde?
Formalin, I think.
Formalin, yeah. You can smell it. You can smell it clear out in the hallway. So it's like
Dead things.
it's diffusing from the cat through the air in the little hallway here, all the way out the door into the hallway. So all of us who walk down the hallway and who eat our lunch near this hallway, we get to enjoy the diffused formalin smell from the dead cats. So let's go talk about why that happens.
Okay. Mr. Sams, that was smelly.
Yeah.
My word. Those biology people, they like make smelly things.
Yeah. If it smells, it's probably
Biology.
biology.
Yeah. Okay. Well, so let's talk about Dalton's Law. Here is actually not Dalton's Law, Graham's Law right here. And this is Mr. Graham. And this is what he said. All right. I forget what Mr. Graham's name is. It's called diffusion. Mr.
Right.
Sams, what is diffusion?
Well, diffusion is when you have a gas, coming
okay.
from one source, and it passes through a medium, and usually that medium is just the air in a room.
Okay.
And as it does that, well, it bumps into these other gas molecules that are in the room, so it takes it a while to get there. Because these molecules.
So if it starts at a point, so we have a source.
Yeah.
Say a dead cat.
A dead cat,
Yeah,
right.
okay. And so then there's gas particles, and they start flying around.
Mm-hmm.
And then some of them... So these gas particles, they're moving around, and eventually, well, they go out in the hallway.
Yeah.
Actually, because they're moving randomly, sometimes they'll back up, but eventually they spread throughout. Let's say this is the room that you're standing in. This is the dead cat right here, DC. Huh, the dead
cat.
Yeah, and those particles eventually spread out through the whole room, and then they stink up the room.
Right. Now, remember these molecules are moving at, like thousands of miles an hour. They're going really, really
be
fast.
Like immediate, though?
Yeah, so it should be pretty much instantaneously, but the fact that they're bumping into the other gas molecules in the room keeps them from getting there instantly.
Yeah. I'm not sure we've really said this or proven this, but just as a side note, folks, I can't talk today, that the molecules move at about 1,000 miles an hour. We said that, I think, in a previous podcast, but there's actually calculations, and we won't do that prove that the average, say, oxygen molecule in the room that we're standing in is moving at about 1,000 miles an hour, which is really kind of amazing, really. All right. So diffusion here is the tendency of molecules to move towards areas of low concentrations. I think we've already said that.
Yeah,
High
everything
to low.
goes from high to low.
High to low. All right. Well, let's move on here. So here is a picture of diffusion.
Right. This is liquid diffusing through another liquid here, but looks like a drop or two of food coloring was dropped in a cup of water, and it's slowly diffusing from an area of high concentration to low concentration until it's uniformly distributed.
Now, one thing else we should say, Mr. Sams, here is in the beaker on the left, or the cup on the left, is filled with hot water.
Oh yeah, look.
And the beaker on the this is filled with cold water.
Yeah, it looks
Can
like
you talk about that, Mr.
Well, it's
Sams?
diffusing faster in the cup on the right because the water is hot. The water is hot, meaning the molecules are moving faster.
Right. And so it can diffuse faster. Yeah. So if we had been in that biology room where it was really, really hot, it would have diffused faster, and the stink would have happened more rapidly into the hallway.
Yeah.
Yeah. Okay. All right. So that's pretty cool. All right. So we're going to continue with Mr. Graham's laws.
Yep.
Okay. And what is the official Graham's law?
Well, the Graham's law of effusion, right?
Now, effusion is a little different.
It's
than
a little
diffusion.
different than diffusion. Now, when we get to the calculations, we calculate them the same way. But effusion is the passing of a gas through a tiny hole.
See, now look at the picture, guys. We have a tiny pinhole here, kind of pinkish here. And if we look at this tiny pink hole, we've got the gas over here, which is the little green dots. And they're going to start traveling through the hole. As you can see, 4 or 5 of them, green dots have passed through.
Yep.
But over time...
over time they'll be the same. And again, it's going from an area of high concentration to an area of low concentration. It'll do so until they're the same. So we have a gas that passes through a tiny hole.
So a process by which a gas goes through a tiny hole. That is what effusion is, as opposed to diffusion, which just spreads out through the whole room or the whole container of whatever.
Right.
Okay. And here's that picture in
It's
zoomed.
big.
It's big. Okay. And so continuing on with Graham's law. Okay. So here's kind of a, because it could also like apply to like perfume.
Yeah, you know, perfume stuff, it drives me crazy. I don't like it. It gives me a headache, and I sneeze a lot when I smell it.
Yeah, yeah.
So never fail. It's like 5 minutes before lunch, and I have a student, pulls out the smelly stuff, puts a little bit on.
Ooh.
Could be a guy, could be a girl.
Nasty.
You never know. And then, you know, like 30 seconds before the bell rings, I start to smell it. Now, I don't smell instantly because, again, it's bumping through all the air molecules.
Yeah.
It gets to me eventually, and just for the rest of lunch, I now have a headache.
So
and
we
I
have this
sneeze really
romance in
badly. Yeah.
Swampland. My darling, little perfume, it's
Mosquito repellent.
mosquito repellent.
Yeah.
By the way, I don't know if you realize, but the background image for this particular podcast is a bottle of perfume. Yeah. Now, Graham's law is not just conceptual.
No, we can do some
It's
math.
also mathematical.
Yay, math!
So how fast does it actually effuse or diffuse? Well, all right. We've learned something recently.
Yeah.
At the same temperature and pressure, they have the same amount of energy. So all gas particles, regardless of what they are, have the same amount of energy. Therefore, where's my pat? Okay. This is still Graham's law. Sorry, I've got some stuff on this fixing here. Okay. Heavy gases go what?
Slower.
So if I have two gases, they have the same energy. So that if you have a big heavy guy, he's going to go slow. That makes the light gases go
Fast.
fast.
Elephant and the bumblebee. The elephant, big
Yep.
mass, nice and
Yeah,
slow.
yeah,
Bumblebee,
yeah.
tiny mass, all over the place.
So which would you like to get hit by, the elephant or the bumblebee?
It depends on which end. I would prefer to be hit by the front end of a bumblebee, but probably, well, maybe not the back end of an elephant either. But
Yeah.
yeah,
It's kind of a weird thing. But actually, the point of this is since they have the same energy, they would actually have, if the bumblebee's going that much faster,
Yeah.
it would hurt you just as much as the slow-moving
right.
elephant.
Although
Yeah.
that would have to be a really fast bumblebee to have the actual same amount of
I
energy.
would think so. Here's some speed. Actually, speaking
Yeah.
of speed,
Hey,
we're
look at
talking
that.
about it. This is in meters per second. But that's a lot of meters per second.
Yeah.
Hydrogen will go at 1,960 meters per
Wow,
second.
because it's tiny, it's light, has a molar mass of 2.
Yeah, molar mass of 2, as you can see down here. Helium is going to go 1,360 meters per second. Oxygen, 490 meters per second. This is equivalent to about, like I said, 1,200 miles an hour or something like that. Something like that. And these guys, of course, are going much faster than that.
Yeah.
So that's pretty cool.
All right,
All right.
so let's do
All right.
some math.
So let's do some math. Okay, so this equation, still Graham's law, can be written. All right, let's write the equation. Here it is, the fancy equation. The rate of A over the rate of B is equal to the square root of
Molar mass.
molar mass of B over A. Now, a thing that students sometimes mix up is the A and the B are opposite each other.
Yes. So A is on the numerator on the left, denominator on the right.
Exactly. And it
Because
doesn't
they're
matter what A or B is.
inversely proportional.
Inversely proportional. So let's do some math on this. Okay, we've got it twice. Okay, so here's a question. At 25 degrees Celsius, helium diffuses at 1,360 meters per second. How fast does propane diffuse?
Okay. Let's
Okay.
use our equation.
Well, let's use our equation. So let's call gas 1. Actually, let me just say something
Yeah.
here. Gas A is best that gas A be
The heaviest one.
Heavier one.
Yeah, the one with the bigger
So
molar mass.
we've got helium here.
That has a
Okay.
molar mass of 4.
4 grams per mole, because that's what it is. And then propane C3H8.
36
that'll
plus
be,
8, 44.
44 grams per mole. Now, where'd you get that, Mr. Sanders?
I just added 3 carbons plus 8 hydrogens.
All right, so let's say A is the propane. I'll just say P. And B is the helium. Okay? So what you're going to do is you're going to say the rate of gas A, okay, this is helium. Okay, so helium goes faster. So he's actually B. So say 1,360 over X. That's what you're trying to find. This is the rate of gas B is equal to the square root of, now it's going to be B. Now that's square root of 44 divided by the square root of 4. Okay?
Right. Again, just put the heavier one over the lighter one.
Right.
The molar mass.
So, I don't think we need to get the calculator out, but so I've got my calculator out here, Mr. Sam. So
Okay.
let's do well, we can say 1,360 over X. I'm going to simplify this term here.
Yeah.
And so I'm going to take the square root. Now the square root button is right here by the X squared. Second function, square root of 44 divided by 4, right?
Yep.
And I close the
Close
parentheses. And I'm going to get 3.32. So that's 3.32 over 1. Now I need to cross multiply, right? So I can say 1,360 times 1, which of course is 1,360, is equal to 3.32x. Now, of course, I divide both sides by 3.32, right?
Yep.
And the 3.32's cancel, so I'll take my 1,360 divided by 3.32, and I get 400. Wow, that's a lot.
410.
410. Yes, so let's call it 410. Now, what does that number mean?
That's the meters per second. That's how fast that the propane molecules are moving.
Right. So that's the rate, the speed at which they travel. One more law, Mr. Sanders, talking about Dalton's law of partial pressure. When this is it, the sum of the partial pressures is equal to the total pressure.
Right. So if we have multiple gases in the same container, the total pressure in the container is equal to the partial pressure of each of those gases added together.
So we could actually put that mathematically like I have right here.
Yep.
The total pressure is equal to the pressure of gas A plus the pressure of gas B plus the pressure of gas C, and if there's a D or an E, the same thing. So if you've got a gas in an enclosed container, you have gas A, which I'll symbolize by black dots, and then gas B by red dots, and we can add the total pressure. It'd probably be easier if we kind of saw this in a different way, Mr. Sams. I think we got a video clip we could probably show them.
Yep.
So let's show them this video clip.
Okay. Okay, we're going to talk about Dalton's law of partial pressure here. Now in here I have 15 of these black balls here, and let's assume they're a gas, and the molecules are going to be flying around, striking the edge of the container, the inside of the container. Now I'd shake them around a whole lot, but I did that a minute ago when we were testing it out, and I broke a very expensive flask. So I'm not going to shake it so much. I'm just going to roll it around, implying that the molecules are moving and bouncing.
So where are they moving, Mr. Sams?
If
they're a gas.
If they're gas, they're flying around at random and striking the inside of the container.
Okay? So they're going up and down, and not just around in
right,
swirls.
all over the place. There's random motion. Okay. Now in here I have 10 of the yellow ones. Okay.
10,
again, moving around in random motion, but I'm not going to do it because I don't want to break another flask. Okay. So let's just say then that these 15 are exerting a pressure of 15 torr. And these 10 are exerting a pressure of 10 torr. And we just want to combine them together. So I'm going to pour the 10 into the 15. I could have poured the 15 into the 10. It doesn't really matter. Okay? Now, again, they're zooming around at random, striking the inside of the container. Now, the combined pressure is simply adding the two pressures together. We had 15 from the black ones, 10 from the yellow ones. So now we have a total of 15 plus 10. 25 torr in this container. Because we simply add the two together, assuming that they have the same volume of container and we're at the same temperature. You just add the pressures together. Dalton's law of partial pressure. Each one exerts a partial pressure, and together their pressures are additive. We just add them up. That's it.
Oops, Mr. Sams, you broke the flask. Oh well, that's okay. It was only $25.
Yeah, you know.
Oh well.
Just take it out of my paycheck.
There we go. So the video clip helped you understand that. So here's kind of a way to kind of look at it mathematically. So here we have a gas. We have 0.6 moles of hydrogen gas in this container, and it has a particular pressure. Okay, a pressure of 2.9 atmospheres.
Okay.
And they can measure that with the weights on the top here. And then we have 1.5 moles of helium gas, and there's more moles of gas, so therefore more pressure, and they have a pressure of 7.2. And now if you mix the gases, this third picture, they're mixed together. Now we have the 0.6 and the 1.5. We end up with 2.1 moles, and we keep the volume the same. We now have 10.1 atmospheres. Now, folks, hopefully you realize if you take 2.9 plus 7.2, it equals
10.1.
10.1.
And again, same volume and same temperature.
Right. It's important. If you change the temperature or the volume, it will change the values. Okay. I think we should probably do one example here.
Okay.
So air is made of 21% oxygen and 79% nitrogen. If the total pressure is 610, what is the partial pressure of each gas?
Okay. So we've got the total.
We've got that equation, P total, P tot, equals the pressure. Now watch how I write this. I say P of O2. I use a subscript, and I'm going to write this symbol, oxygen, plus P N2. But I can't really add them because I just have percentages.
Okay, so let's do that. Well, just take 21% of 610 and then 79%
of So
610.
if I've got 610 torr, a millimeter of mercury is equal to torr, and I times it by 20% or 21%, folks, that's actually 0.21 when you do that as a decimal. So we don't probably need to show you the calculator, but Mr. Sams is fiercely typing.
And 128.1.
128.1 torr.
So that's the pressure being exerted by oxygen.
So that's the pressure of O2. And if I then take 610 torr and I times it by 0.79, that's 79% rendered as a decimal, I'm going to get
481.9.
481.9 torr. And that's the pressure of the nitrogen. Just for grins, if you were to take these two numbers and add them up, what would you get?
610.
610 torr. So if you got a percentage, you got to be a little bit more creative, but it really is the same principle.
Right.
You just have to understand the concept of how percentages work, guys. It's really not terribly difficult. Now we need to kind of end with one thing. One of the most important applications of Dalton's law is when we're collecting a gas, which we're going to be doing in an experiment,
or 2 or 3.
or 3 or 10. Lots of experiments for the rest of the year. So when you collect a gas over water, you need to subtract what's called the water vapor pressure, because there are two gases. Now, let's take a look at a picture here that will help us illustrate that. So in this particular flask, I have sulfuric acid, I guess, and zinc. When they react, they produce hydrogen gas. The hydrogen gas goes through the tube. We've collected gases before, right, ladies and gentlemen? And it produces the hydrogen gas, and it fills this up. Now, the key thing to understand is in this flask, as it sort of says here in the picture, there's both hydrogen gas and water gas, better known as water vapor. And so when you're doing math for this...
where did the water come from?
Well, since it's bubbling through the water down here, some of that water will evaporate.
Right. We're basically dealing with the vapor pressure of water is what
Yes,
we're working with there.
which we've talked about in the last unit.
Right.
And so there's some vapor pressure. So we need to essentially get rid of that, because you see the total pressure will be equal to the pressure of the hydrogen gas plus the pressure of the water in this case.
Right. And when we're collecting gas, we're only concerned with the pressure of the gas we're generating.
Typically, we're only interested in this value. Now, the total pressure can be read from a barometer.
Yeah, so whatever the atmospheric pressure is outside, we'll teach you how to equalize the tube later on so that the pressure inside the flask is equal to the pressure outside, and so the pressure are the same.
So let's take a look at this. Here's another way to look. Here's, yeah, we don't need that. This is what I want. So if I have, this is called the water vapor pressure table, and you're going to have this in your packet, and you're going to want to cut it out.
Cut it out, paste it in your count book.
Paste it in your
it's
count
also
book.
on our cupboards, so you can look it up in the room.
Yeah, lots of places you're going to have access to it. So if you know the particular temperature, let's say you're at 20 degrees Celsius, then the vapor pressure is 17.5. This is in torr, by the way, or millimeters of mercury. So if I go back to my picture here, so let's say you're at 20 degrees Celsius. So let's say that we go to our barometer. We find the pressure is 590 torr, which would be pretty typical in Woodland Park. Okay, if you're watching this somewhere else, you probably have a torr typically 760. You're probably closer to sea level. We live way above sea level. So if we are at 20 degrees Celsius, I would look that up on that table. And that number was 17.5. So the pressure of the water is 17.5. So you subtract, we'll just say 18 for sig fig. And so this is the total pressure. This is the pressure of the water. And if you subtract that, you'll get the pressure of the hydrogen.
572.
It's just 572 torr. And why is that important? When you take this number, the 572, you're going to use that in your equation with PIVNER, or ideal gas law, P equals nRT. You're not going to use the 590. You're going to use the 572, and actually you'll have to convert that to atmospheres or whatever, and we'll talk about that in the next podcast. But you have to subtract the water pressure, and it is a application of
Dalton's
Mr. Johnny
law
Dalton's law
of breaking the flasks.
Yes, the Dalton's law of breaking the flask. So, hey, I think we're done with this podcast, Mr. Sands.
Yeah, good thing, because I got some glass to clean up.
Yes, all right. Well, good. Bye.